So in this video, we're going to talk about section 2 of chapter 6, which deals with area. Now, I know in geometry, you talked about area and everything like that, but we're going to kick it up a notch here with this lesson. So we're going to use sigma notation to write and evaluate a sum, understand the concept of area, use rectangles to approximate the area of a plane region, find the area of a plane region using limits. So first, let's talk about what sigma notation is. So we've studied anti-differentiation. In this section, we're going to look further into a problem, and that is finding the area of a region in the plane. First glance, these two ideas may seem unrelated, but you will discover that they are closely related by an extremely important theorem called the fundamental theorem of calculus. This section begins by introducing a concise notation for sums. This notation is called sigma notation because it uses the uppercase Greek letter sigma, written as this. So here's what sigma notation is. If you add a sequence of terms, so A1, A2, A3, so forth and so on, and there's some kind of pattern to it, where I is the index of summation, A is the ith term of the sum, and the upper and lower bounds of the summation are n and 1. So I equals 1 means you start on the first term, the upper bound is n, that's the number on top, and that means the number you start at. So if it's I equals 1 to say 5, that means there's going to be terms 1 through 5. And this A sub I is the general term. It's the general way to get each term. And you get each term by plugging, start at the number of the lower bound. So in this case, start at 1, plug it in, what you get, that would be the first term. Then go to 2, plug in 2, get it, that would be your second term. 3, that would be your third term, and so forth and so on, all the way up to whatever term it says to stop on. You add all those up, and that's what the answer is. Okay, so the sum of I, as I goes from 1 to 6, is just, you just plug 1 through 6 in for I and add them together. 1, 2, 3, 4, 5, 6. Okay, if it's I plus 1, and you got I equals 0 to 5, you start at 0 and go up to 5 and plug in I plus 1. So it'd be 0 plus 1 is the first term, 0 plus 1 is the second, or 1 plus 1 is the second term, 2 plus 1, 3 plus 1, 4 plus 1, 5 plus 1, so forth and so on. You can make them as complicated as you want. Sometimes they change the index of summation. Most commonly, they use I, J, and K. So it's kind of like variables X, Y, and Z in functions. So J equals 3 to 7. That means you start at 3 and go up to 7. So the formula is J squared. So you go 3 squared, 4 squared, 5 squared, 6 squared, 7 squared. Add those up. But this is just expanding the sum, writing it out. So this notation right here is the summation notation, and that's a compact way of writing this big long sum. Now the nice thing about it is if you had like 500 terms, you could write the summation in just one little thing like this, one little compact notation, rather than having 500 terms all the way out. And you can make them as complicated as you want. Notice a couple things here. This is the sum is k goes from 1 to n, and the formula is 1 over n times k squared plus 1. Now, I know there's 2 letters in here. So this is a general formula that you can use depending on what the upper bound is. So you'd always start at 1 and go to whatever n is. So the formula, like if n was 10, they'd all have a 1/10 in the front. If n was 15, they'd all have a 1/15. Okay? And then you go from 1 to 15. But you started out, it'd be 1 over whatever n is times k squared plus 1, so 1 squared plus 1, and then you do the same thing with 2 all the way up until you get to whatever n is. Okay? This is another one. So again, all you do is just copy the thing down and plug in the numbers from 1 to whatever n is, wherever the I is. So if it's this, you would read this f of x sub I times delta x. That's the formula. Well, you plug in 1, f of x sub 1, delta x. Plug in 2, f of x sub 2, delta x, all the way up to f of x sub n, delta x, and add those together. From parts A and B, notice that the same sum can be represented in different ways using sigma notation. Although any variable can be used as the index of summation, I, J, and K are often used. Notice in example 1 that the index of summation does not appear in the terms of the expanded sum. Let me back up and show you what I'm talking about. The I does not appear in the terms because you're substituting 1 through 6 in for I. The following properties of summation can be derived using the associative and commutative properties of addition and distributive property of multiplication over addition. In the first property, k is a constant. So if you have a constant times the sum formula, you can factor the constant out. That's because the a sub I is just a whole bunch of things added together, and you're multiplying each one by k. Well, if you work them all out and you're multiplying each one by k, it's like you distributed a k to all of them, so you could factor the k out and multiply it at the end. Here, you're adding or subtracting. It's a sum or difference of two indexes or two terms. So you can add or subtract their sums. Think about it. If you wrote it all out, you would have a1 plus b1 plus a2 plus b2 plus a3 plus b3 plus so forth and so on. Well, you can regroup those by the properties of addition and add all the a's first and add all the b's first, and that would just be like adding the sum of a first and adding the sum of b first. Same thing for subtraction. Now here's some useful formulas for sums of powers, and you're going to want to use these as we progress through this section. This is the sum of a constant. Notice the index of summation is I, but C is the formula. So that would be like the sum of I equals 1 to 6 of 4. That means the first term is just going to be 4 plus 4 plus 4 plus 4 plus 4 plus 4, because there's no index of summation. Okay? Just a constant. Well, if the sum starts at 1 and it goes to n, like in this case, it started at 1 and went to 6, you're just adding 6 4s together. Well, that's like quick addition is multiplication, so 6 times 4. Okay? This is the sum of the integers. So notice if I starts at 1 and goes to n, if you wrote it out, it'd be 1 plus 2 plus 3 plus 4 plus 5, all the way up to whatever. Well, whatever n is, there's actually a formula to figure out the sum of all of that real quickly. It's just you multiply n times 1 more than n, and then divide that answer by 2. And there's a formula if you're adding the first squares of integers and the first cubes of integers. I will say that the formula for squares is a little bit more complicated, but like if you knew n was 10, you would have 10 times 11 times 21 divided by 6. Okay? And then the formula for I cubed, now look at it. It's everything as the formula for I, but you're squaring everything. Is n squared, n plus 1, quantity squared. 2 squared is 4. Okay, so sometimes you'll see it written as n times n plus 1 over 2 quantity squared. Now, most common mistake I see students do is they use this one for the I squared formula because it's the I formula. It's the formula for I squared, but really it's the formula for I cubed. Okay, so just make that distinction in your mind. All right, so let's evaluate I plus 1 over n squared for n equals 10, 100, 1,000, and 10,000. So in this formula, I is the index of summation. Any other letters would be understood to be constant. So by theorem 6.2, you can take the over n squared out as a 1 over n squared, factor that out. And then you have I plus 1. Then, since it's a sum of two different things, you can rewrite it as two different sums. Okay? Then you can use the formula for the sum of I and the formula for the sum of a constant. So it's 1 over n squared times the sum formula for I, which is n times n plus 1 over 2. The sum formula for constant, which is the constant times n. Here the constant's 1, so it's just 1 times n. Okay? So we've used the summation formulas to simplify this. Otherwise, you're going to have to plug in 1 through 10 to add those up, then plug in 1 through 100, add those up, 1 through 1,000, add those up, and through 10,000, add those up. Anything above 10 is going to be a whole lot of work. So I could take this formula and simplify it. Now, whoa, what happened there? Well, if you write this n as 2n over 2, now you have a common denominator, and you can add those together. So it would really be n squared plus n plus 2n over 2. I distributed the n here to get n squared plus n, and the n in this n right here, I rewrote as an equivalent fraction of 2n over 2 to get the common denominator here, so that's the 2n over 2 there. Okay, remember I just did that? Well, the n and 2n make 3n, all right? And then if I could factor out an n from both of those and make it n times n plus 3. And then this factor of n cancels with the n squared there, making it just n. So when I multiply it over, it just becomes n plus 3 over 2n. So now you can just plug that into your calculator and use the table feature and plug in 10, 100,000, 10,000. And you can see that it looks like as n approaches infinity, the limit is going to be a half as n gets larger and larger and larger. Pretty cool stuff. All right, so in the table, note that the sum appears to approach a limit as n increases. Although the discussion of limits at infinity applies to variable x, where x can be any real number, many of the same results hold true for limits involving the variable n, where n is restricted to positive integer values. So to find the limit of n plus 3 over 2n as n approaches infinity, you can just write it as a limit and break it apart into two separate fractions. Reduce each fraction, let n approach infinity. This term goes off to 0. The limit of a constant is the constant, so 1/2 plus 0 is half. Pretty cool stuff there. I hope that wasn't too heavy for you. All right, see you in the next video.